Because the aforementioned critical constants are the state variables of a gas at its critical point, we will examine this special state for von der Waals gases. In the equation of state of a von der Waals gas, the pressure P of the gas is expressed by the gas constant R times the absolute temperature T of the gas over the difference between the molar volume Vm of the gas and its volume correction constant B, minus the pressure correction constant A of the gas over the square of its molar volume Vm. Since the correction constants A and B depend on the properties of the gas, the pressure of different gases will be a different function of the molar volume at a constant temperature, as opposed to an ideal gas. That is, the isotherms of the equation of state are different for each substance. In order to illustrate the difference, we will give different examples for the pressure versus volume diagram of three types of gases by plotting their isotherms over a wide range of temperature. The first example is the hydrogen gas with the von der Waals constants A equals 0.2453 bar liter squared per mole squared, and B equals 0.02651 liter per mole. Here we plotted the isotherms of the gas in the pressure versus molar volume diagram for the range of temperature between 12 Kelvin and 92 Kelvin with the temperature intervals of 2 Kelvin. In the second example we show the isotherms of the oxygen gas with the von der Waals constants A equals 1.382 bar liter squared per mole squared, and B equals 0.03186 liter per mole. For oxygen the temperature already covers a greater range between 55 Kelvin and 365 Kelvin, and the isotherms are drawn in 10 Kelvin intervals. The isotherms in the third example are plotted for the butane gas with the von der Waals constants A equals 13.89 bar liter squared per mole squared, and B equals 0.1164 liter per mole. In the plot the range of temperature shifted to even higher temperatures in the range between 165 Kelvin and 1105 Kelvin with the temperature intervals of 20 Kelvin. Although the scales in these three pressure versus volume diagrams are different due to the different von der Waals constants, the structure of the family of isotherms is determined by the mathematical form of the equation of state, which is the same in each case. We can see a critical isotherm plotted with red color separating two sets of isotherms in each diagram. This critical isotherm at a critical temperature Tc has one point of inflection which is called the critical point of the von der Waals gas. The critical temperature is 33.3 Kelvin for hydrogen, 154.8 Kelvin for oxygen, and 425.1 Kelvin for butane. The green and yellow regions cover the two set of isotherms separated by the critical isotherm in the pressure versus volume diagrams, where we also show the critical point K of the von der Waals gas, that is the point of inflection on the critical isotherm. The first set of isotherms running in the green region belong to temperatures greater than the critical temperature Tc of the gas. The common properties of these isotherms are the following. All of them are monotonic decreasing functions of the volume of the gas, and they approximate hyperbolas with increasing temperature. This shows that at low pressure and high temperature a von der Waals gas acts as an ideal gas. It is important to mention the condition for low pressure since the vertical asymptote of the hyperbolas is not located at the volume equals 0 line. There is a minimum volume which a given amount of gas composed of molecules with finite size can be compressed in the von der Waals model, described by the volume correction constant B of the gas. The second set of isotherms running in the yellow region belong to temperatures lower than the critical temperature Tc of the gas. These isotherms have a local minimum and a local maximum which approach each other with increasing temperature, and merge in the point of inflection that is in the critical point K at the critical temperature. As a result, the isotherms monotonically increase in the region between their local minimum and maximum, depicted by the orange areas in the diagrams. In this region the pressure of the gas increases with its volume at a constant temperature, which cannot be a physical state of a real gas, indicating that it is an unstable region for the von der Waals model. This is the region of the phase transition between gas or vapor and liquid, and the critical point K determines where the medium can exist in a multi-phase state in the pressure versus volume diagram. Now we determine the state variables, that is the temperature, pressure and volume of a von der Waals gas in the critical point K of the gas. Because the critical point is a point of inflection of the pressure as a function of the volume, its first and second order derivatives with respect to the molar volume at a constant temperature vanish in the critical point. If we substitute the expression for the pressure P of the von der Waals gas into its first order derivative with respect to the molar volume Vm at a constant temperature T, we obtain minus the gas constant R times the temperature T over the square of the difference between the molar volume Vm and the volume correction constant B, plus 2 times the pressure correction constant A over the cube of Vm. This expression must be 0 in the critical point K. Similarly, the second-order derivative of the pressure P with respect to the molar volume Vm at a constant temperature T is given by 2 times R times T over the cube of the difference between Vm and B, minus 6 times A over Vm raised to the power of 4. This expression also vanishes in the critical point K. We can move the second terms in the left-hand side to the right-hand side of both the equations, and divide the first equation by the second one. This gives an equation stating that the difference between Vm and B divided by 2 is equal to Vm over 3. Now we can express the molar volume Vm at the critical point from this result as 3 times the volume correction constant B of the von der Waals gas. This quantity called critical volume V sub mc can also be given by 3 times the amount of species and the gas times B, denoted by Vc and measured in cubic meter. We have expressed the critical volume of a von der Waals gas in terms of a von der Waals constant, and we can do the same with the critical temperature as well. If we evaluate the vanishing first-order derivative of the pressure with respect to the molar volume and the critical point, then we can write the equation stating that minus the gas constant R times the critical temperature Tc over the square of the difference between the critical molar volume V sub mc and the constant B, plus 2 times the constant A over the cube of V sub mc is equal to 0. Here the critical molar volume V sub mc is given by 3 times B, which we substitute for the derivative. As a result, we obtain another equation stating that R times Tc over 4b squared is equal to 2 times A over 27 times b cubed. By solving it for Tc, we can express it as 8 times A over 27 times b times R. In order to express the pressure in the critical point in terms of the constants A and B, we can use the equation of state evaluated in the critical point, which states that critical pressure Pc is equal to R times the critical temperature Tc over the difference between the critical molar volume V sub mc and the constant B, minus the constant A over V sub mc squared. Now we insert the critical molar volume and the critical temperature expressed in terms of the von der Waals constants into the equation of state evaluated in the critical point. After simplifying the two terms in the right-hand side, we obtain 4 times A over 27 times b squared, minus A over 9 times b squared, which gives A over 27 times b squared. We conclude that the critical constants of a von der Waals gas are the following. The critical temperature Tc of the gas is equal to 8 times the pressure correction constant A over 27 times the volume correction constant B times the universal gas constant R. The critical pressure Pc of the gas is given by the pressure correction constant A over 27 times the square of the volume correction constant B. The critical molar volume V sub mc of the gas is equal to 3 times the volume correction constant B, or alternatively the critical volume Vc is given by 3 times the amount of species N of the gas times the constant B. We note again that the critical constants of a von der Waals gas are its state variables in its critical point, which is a unique physical state represented by the point of inflection on the critical isotherm of the gas. We already mentioned in the discussion on the von der Waals constants that the critical pressure of a substance is required to liquefy a gas at its critical temperature. This means that the critical point designate the top of the unstable region in the pressure versus volume diagram, where the critical phenomenon of phase transition of a gas can take place and where liquid and gas coexist. We also mentioned in the previous section that the von der Waals constants of a gas can be determined from its critical constants. We immediately see that the volume correction constant B can be expressed by 1 over 3 times the critical molar volume V sub mc, whereas the pressure correction constant A is equal to 27 times B squared times the critical pressure Pc. The later can also be written as 3 times the square of 3 times B, times Pc, that is 3 times V sub mc squared times Pc. Instead of pressure, we can write the constant A in terms of temperature by using the formula obtained for the critical temperature. Then we have 27 times B over 8, times R times Tc, or 9 over 8 times V sub mc times R times Tc. These expressions show that we can determine the von der Waals constants of a real gas, which are essentially parameters emerging from a theory of approximating the behavior of the gas, if we are able to measure the critical constants of the real gas. Now we look at how to determine the critical point of any substance, that is to measure its critical constants. Such a measurement is performed by using a so-called critical point apparatus shown in the photos with 2 different implementations. It is a high-precision device for studying the compression and liquefaction of a gas and recording its isotherms in the pressure versus volume diagram. The apparatus includes a transparent measuring cell which is highly resistant to leakage and compression, enclosed in a transparent water chamber serving as a part of a thermostat. The volume inside the cell can be changed via a finely adjustable handwheel for both the types of devices. The apparatus in the first photo uses a capillary as the measuring cell made from an extremely strength glass, and a glass cylinder as a water chamber. The lower meniscus of a mercury column in the capillary shows the position that can be read for the determination of the volume. The mercury is supplied from a stainless steel pressure chamber sealed to the measuring capillary. For the apparatus seen in the second photo, the change in the volume of the measuring cell is indicated by a combination of a fixed and a rotary scale to a high accuracy. The device uses hydraulic oil instead of mercury, where the measuring cell and the hydraulic system is separated by a membrane that moves as the volume of the cell increases. A thermostat circulating the water in the water chamber allows the temperature to be maintained at a highly constant value in the measuring cell of both the types of apparatus, which can be monitored by means of a thermometer. After setting the temperature of the thermostat and allowing temperature equalization between the water bath and the gas to take place, the temperature of the system can be read from the scale of the thermometer. In the first apparatus, the pressure chamber must be filled with the sample gas and its pressure is measured by a manometer. In the second apparatus, the pressure is the output of the hydraulic system, since the pressure gradient between the measuring cell and the chamber of oil is negligible. The determination of the critical point and the state variables of the sample in the critical point is the following. In the case of the first apparatus, the pressure chamber can be filled with the sample by connecting it with the container of the sample gas and opening its inlet valve. In order to clean any residues of gas from the pressure chamber, it must be evacuated for at least 30 minutes, which removes the gas dissolved in the mercury. By turning the hand wheel, the gas will be compressed until the mercury column is visible in the measuring capillary. With suitable gases, an increasing liquefaction of the gas can be seen above the mercury meniscus on increasing compression. In the case of the second apparatus, we have a similar procedure. After the gas container of the sample is attached to the device, the measurement cell must be flushed several times with the sample gas to eliminate air from the system. At the beginning of the measurement, the inlet valve is closed and the volume of the measuring cell is set to a given value. At the initial volume, the inlet valve is open to fill the cell and reach an initial pressure. Then the valve can be closed and the hand wheel can be turned to decrease the volume of the cell while monitoring the increasing pressure. The volume of the compressed gas in the cell is read from the combined fixed and rotary scale when the gas starts to liquefy in the transparent measuring cell. The measurement with these devices is based on visual information, since it is possible to observe the formation of the first drops of liquid and disappearance of the last gas bubbles during transitions from the gaseous to the liquid phases and vice versa. During the phase transition, the critical volume can be determined from the height of the mercury column or the position of the combined scale on the measuring cell. The corresponding pressure values are indicated by the manometer measuring the pressure of the cell. The critical temperature can also be determined by controlling the thermostat to find the minimum temperature above which no phase transition is detected for arbitrary compression of the gas. In such a way, the state variables of a given amount of gas, that is its critical temperature, pressure and volume, can be measured by the apparatus when the phase transition of gas is observed in its critical point. Before presenting some data as a result of the measurement of the critical constants of various substances, we introduce the critical compressibility factor of the gaseous phase of a medium, which is simply its compressibility factor determined in its critical point. That is, the critical compressibility factor ZC of a gas is defined by the product of the critical pressure PC and the critical volume V sub MC over the product of the gas constant R and the critical temperature TC, where all the critical constants are measured for the given gas. If we apply this definition for a von der Waals gas, we can substitute the critical constants expressed in terms of the von der Waals constants. Then ZC is given by 1 over the gas constant R, times the pressure correction constant A over 27 times the square of the volume correction constant B, times 3 times B, times 27 times or times B over 8 times A. This gives 3 over 8, that is, the critical compressibility factor ZC in the von der Waals approximation is equal to 0.375. Showing the critical compressibility factor is universal for all von der Waals gases. This table contains the critical constants of the substances already used to illustrate the variation in the von der Waals constants between different types of gases. The figures in the table show that the critical constants tend to increase with the size of the molecules. It is helium with its monoatomic molecule that has a compact structure with the lowest critical constants in the table. Its critical temperature is about 5 Kelvin, its critical pressure is less than 1 megapascal, and its critical molar volume is only somewhat greater than 0.05 cubic meter per kilomole. All the critical constants are greater for the gas composed by hydrogen molecules. Its critical temperature and critical pressure are already 1 order of magnitude greater than those of the helium, and its critical molar volume is also greater than 0.06 cubic meter per kilomole. By considering molecules of elements that have greater atomic numbers in the periodic table like oxygen, nitrogen, and bromine, we see that the critical temperatures are 1 order of magnitude greater than those of the light elements. Their critical pressures are also several times larger than the critical pressure for the hydrogen molecule. There is some increase in their critical volume as well, but it is much more moderate. Indeed, their volume correction constants are not much greater than those for the molecules of light elements. Not surprisingly, the water molecule has even higher critical temperature and critical pressure, although its critical molar volume remains very small. In the case of substances composed of organic molecules like alkanes, we find that butane, octane and decane have somewhat lower critical temperatures than water, and their critical pressures remain in the range of the critical pressures of oxygen and nitrogen. Nevertheless, their critical molar volumes are at least one order of magnitude greater than those of the other substances shown in the table, indicating that their volume correction constants are also the greatest among them. We also display the critical compressibility factors EC for each substance in the last column of the table. By comparing the values in this column with the value computed from the von der Waals equation, we can see that the values measured for the real gases are always less than the one derived for von der Waals gases. This deviation simply indicates the fact that the von der Waals gas is only an approximation describing the behavior of real gases. Because the deviations are smaller for gases composed by lighter molecules than for heavier elements or more complex molecules, we conclude that the approximation is more accurate for molecules with more compact structures. We have already seen that the equation of state for a von der Waals gas is a cubic equation in the volume of the gas, which expresses the pressure P of the gas as the gas constant R times the temperature T of the gas over the difference between the molar volume Vm of the gas and the volume correction constant B, minus the pressure correction constant A over Vm squared. If we multiply this equation by the difference between Vm and B, and factor out the parentheses, then we obtain the cubic equation stating that Vm cubed, minus the sum of B and R times T over P times Vm squared, plus A over P times Vm, minus A times B over P is equal to 0. In this equation the von der Waals constants are fixed for a given gas, and the temperature determines which isotherm is considered in the pressure versus volume diagram. As we have already discussed and as the isotherms for hydrogen show, the solutions of this algebraic equation can be separated into two, or including the critical isotherm, three classes. If we consider temperatures greater than the critical temperature Tc of the gas, then the equation have one real root. For the critical isotherm where the temperature is equal to Tc, the cubic equation has triple roots, that is three roots that are equal, whereas in the case of temperatures less than the critical temperature we will find three different roots. Because the critical point of a von der Waals gas is a point of inflection of its critical isotherm, the cubic equation has triple roots in the critical point. The value of the triple roots is the critical molar volume V sub mc of the von der Waals gas. As a result, we can write that the cube of the difference between the molar volume Vm of the gas and its critical molar volume V sub mc, that is Vm cubed, minus 3 times V sub mc times Vm squared, plus 3 times V sub mc squared times Vm, minus V sub mc cubed is equal to 0. By comparing this equation with the one above evaluated in the critical point, we can identify the multiplication factors in the two equations as follows. 3 times V sub mc must be equal to B plus or times Tc over Pc, 3 times V sub mc squared must be given by A over Pc, and V sub mc cubed must be equal to A times B over Pc. We can express the pressure correction constant A from the second relation as 3 times V sub mc squared times Pc, which we already derived from the conditions of the vanishing first and second order derivatives of the von der Waals equation in the critical point. If we substitute this result into the third relation, we can write the cube of V sub mc as 3 times V sub mc squared times Pc times B, over Pc, that is 3 times V sub mc squared times B. Then we express the critical volume V sub mc as 3 times the volume correction constant B again. By inserting this formula into the first relation and solving it for Tc, we obtain the ratio of 8 times A over 27 times R times B, as expected. Here we have just re-established that the relations between the critical and von der Waals constants of a gas allow one to determine the von der Waals constants of a gas by measuring its critical constants. Now we examine the class of the solutions to the cubic equation for which the temperature is less than the critical temperature. Since the equation has three different roots in the region indicated by the yellow and the orange areas, each isotherm has a point of inflection between a local minimum and a local maximum. This fact has already been established from the isotherms of hydrogen, oxygen and butane, and we also saw that minima and maxima of the isotherms enclose an unstable region indicated by the orange area in the diagram. In the unstable region the pressure increases with volume, that is, the gas has a negative compressibility. This means that any isotherm passing through this region cannot be an equilibrium state for the gas or the substance. As the measurements performed by any critical point apparatus demonstrate, a gas-liquid phase coexist in the unstable region. A continuous phase transition can be observed between gases or vapors and fluids while the pressure stays constant. When the phase transition is complete, the pressure starts to change at a given volume. It will increase after a complete liquefaction and decrease after a complete vaporization of the medium.